Hey everyone, welcome back to Stat and Research 2. This week we're going to have two lessons. Lesson 5 on Latin squares designs, which we'll start talking about right after this intro. Then the second one is unbalanced designs, which we'll start after talking about Latin squares. Both lessons have 3 videos, but we only have one homework due Saturday at midnight. Now, before starting the Latin square design lecture, there are 2 big class announcements. First, let's go to when the midterm is, just so we are all on the same page. Right now, we're in the week of February 15th through the 19th, so we'll be talking about the Latin square and unbalanced designs. Then the next 2 weeks will be focused on factorial and subsampling, where you'll have homeworks due Saturdays. The week after that, March 8th through 12th, we will have a midterm. You will have the entire Monday through Friday to take the midterm. But once you start the midterm, you will only have a specific amount of time. Right now, I'm still not sure how much time it is. I don't know the exact time. It'll be between an hour and a half and 2. But as we get closer, I'll hold a review session the week of March 1st through 5th so we can get all these questions out, make sure you guys are all on the same page and you feel prepared going into the midterm. Additionally, I will also hold my office hours Tuesday, Wednesday, Thursday from 10 to 11 the week of the midterm, just in case you're getting those butterflies or a little bit of anxiety and you just want to ask me a question of clarification before taking it. So with that, I also want you guys to feel prepared for the midterm. And so far, our homeworks have only kind of had one problem for each type of design we've talked about. So to help you guys feel confident and feel like you're being prepared for the exam, I have also created practice problems. So it's this pretty 6-page document where I'll give you data sets and you're going to apply and answer these questions. What I will do to hopefully motivate you guys to do these practice problems, and hopefully that will help inspire some questions if you guys have any, or it will be like, yep, I understand this concept, I'm good to go, is on Canvas, I will have a label called Practice Problem Set 1. And what I'm going to do, or what I would expect you guys to do, if you want to, this is an extra credit opportunity. This is what I'm trying to say. It's an extra credit opportunity where if you complete the entire document, every question to the best of your ability, and I would expect it to at least get 95% of the problems correct, you guys are going to have some mistakes. And again, you can come to office hours if you have questions. But if you do these practice problems, write them up nicely so it's easy for me and the TA to grade quickly, I'll give you a complete. And what a complete means is that I will add 10 points to a homework assignment. And so hopefully that will motivate you guys. It's a little bit extra credit, help you practice for the exam that's coming up very soon. And I think that's all my class's announcements. If there's any questions or concerns, please message on Slack or come to office hours. So with that, let's start lesson 5A where we're talking about Latin squares. So in this lesson, we'll be covering the Latin square design by talking about the definition through an example, how to apply a randomization scheme to ensure we have a valid Latin square design. And then we'll talk about the summary statistics, the model, and the ANOVA table for the Latin square design. In our next lecture, we'll actually apply this to the spreadsheet example that we're talking about right now using our various softwares. So before we talk about the Latin square, let's just quickly recap the designs that we've covered thus far. The first one was the completely randomized design, where we have one treatment factor and one block, or no block. Then we went to the randomized complete block design, where we had one treatment, one block, and only one replication per treatment block combination. Then we went to the generalized random complete block design, where we had one treatment, one block, and we had multiple replications per treatment block combo, which allowed us to estimate the interaction term. And we talked about that in our last videos last week. Now we're going to start talking about the Latin square design, which has one treatment factor, just like our other designs, but now we're going to have two blocking factors that are crossed. And this is a special design that's not going to be able to fit every situation, but if you can do a Latin square design, it's really, really good because it's going to help us not waste resources. I'll talk more about that a little bit later in this section. We also have interlocked blockwise randomization, and this will make more sense as we start to see an example. For the parameters of the Latin square design, you'll notice that we have T treatments, and now we have what we call T row blocks and T column blocks. And rows and columns are relating back to the fact that the Latin square design is being a square design. And we'll talk more about this, but the term row and column is very kind of arbitrary, and that will make sense as we get to the example as well. Note that we also have this restriction that we have T treatments, T number of row blocks, and our T number of column blocks. And this is what's going to make the restriction that our total number of EUs is T squared and not T cubed. Okay. So let's get to an example so that hopefully more of these characteristics and parameterizations will make sense to you. So a law firm is trying to determine which of 4 spreadsheets from well-known software companies is the easiest to learn for their secretaries. Learning time is known to depend on individual secretaries and the type of tasks. 4 secretaries and 4 tasks are selected. The law firm wants their secretaries to spend as little time as possible on this experiment. Okay, so what's our response? Our response will be the learning time. Our treatment factor or treatments is the spreadsheet. Because this is what we're testing, and we'll just label these A, B, C, and D. And then what are our blocking factors? So we know for Latin square, we're going to have 2 blocking factors, where the idea of blocking is to help. And remember, the idea of blocking is to manage extra systematic variability besides the treatment, besides just the treatment. And so in this case, we have one thing that we want to be able to block for is our secretary. So secretary is one blocking factor. And then also our tasks are our next. We're going to label our tasks I, 2, 3 Roman numeral, and then 4 Roman numeral. Our secretaries are going to be 1, 2, 3, 4. And just to give you guys an idea of tasks, maybe task 1's accounting, task 2 is doing something with data tables, task 3 is doing summary statistics, and maybe task 4 is doing graphics. So in this setup, again, we have 4 secretaries, 4 tasks, and we're not necessarily interested in the secretary to secretary variability, but we want to be able to block for it. And we also realize that our task is going to potentially differ in time. So we want to be able to block for that. So that's why we have 2 blocking factors. So far, we've only talked about RCBDs or GRCBDs, where we were only considering 1 blocking factor. So let's do this real quick to show where this could potentially cause some issues and why we want to introduce maybe a second block. Let's say we're going to keep secretary as our block, and we're just going to ignore task as a blocking factor. We're not worried about it right now. And we apply our randomization scheme for a RCBD, and we can see that each block of the secretary has A, B, D, C, A, B, C, D. And so it's going to, this is characterized as a RCBD. Now, let's say we had additional information where task 1, which is, let's say, accounting, is the most time consuming. And task 4, which is graphics, would be the least consuming to complete. One of our limitations with this representation using an RCBD is that we see 3 out of the 4 secretaries are using spreadsheet C with task 4. So right here, we have 3 secretaries using task 4 with spreadsheet C. So the influence of the type of task on time needed to complete the task is going to create a problem. Also, this design will probably unfairly promote spreadsheet C, since spreadsheet C is used 3 times with the quicker or faster task of graphing or task 4. So here's the question we would probably want to ask ourselves is spreadsheet C really better? Or is it just because the secretaries are using task 4? And so similar to why we introduced RCBDs in lesson 3, by blocking out extra sources of variability, it also will be beneficial in this case to block out tasks so that task 4 is not used 3 times by spreadsheet 3 or C. So again, this is going to motivate us into our Latin square solution. Our Latin square solution is going to incorporate 2 blocking factors, and a really good part, and the reason why Latin squares are a good design is because it's going to minimize our number of EUs. So we can do this design with a very small number of observations, which is efficient use of resources. So one of the goals in experimental designs isn't only just to create a design that helps us see if our treatments differ, but it's also the ability to get an effect of our treatment without wasting a bunch of resources, because time and money are constraints as well that we need to incorporate and think about when we are doing our designs. So the Latin square solution would look something like this, where now we have our task as a block and we have our secretary as a block. And so the difference between the Latin square and the RCBD is that each treatment for the Latin square appears once in each row and exactly once in each column. So if we look here, we see A only appears once in this column and A appears only once in this row. The best way of thinking about a Latin square design is like it's a Sudoku problem, where only one treatment, this treatment can only be in this row and this column. And as you go through, you'll start to notice that. So for our spreadsheet example, each spreadsheet is used by one task and one secretary, which you see. Now that we've laid down the idea of a Latin square, that we're able to use these 2 blocking factors with one treatment, let's talk about randomization. Before I talk about randomization, I just want to also remind you that I said that row and column is a very arbitrary sense. I could have easily taken secretary and put it here, and we had 1, 2, 3, 4, and task up here and put in Roman numerals 1, 2, 3, 4. So it doesn't matter which way you lay this in this case. Okay, so let's talk about randomization for a Latin square. So this would be I guess the best word would probably be is algorithm to ensure you have a randomized Latin square. So you're going to start off with a standard layout where we're going to put treatment A, B, C, all the way to T. I'm assuming we have cap T treatments. Okay. In our next row, we're then going to go B, C, D. Our T-1 column will have T and then A. And you repeat that. This S, just for clarification, is coming because in the alphabet, it's ST. And so this is representing S represents the T-1 treatment. I'll have an example in one moment to hopefully help demonstrate this a little bit better. Once we have this standardized layout, which is going to ensure we have a Latin square design, we're going to permute the columns in rows, and then we're going to replace the old columns and rearrange it such that it looks nice. Let's go to an example because it will make a lot more sense. So here's an example. In our example, we're going to assume that T is equal to 5. So we have 5 treatments in which we have A, B, C, D, E. So step 1 is to do our standard layout where we just lay out all the treatments. So A, B, C, D, E. Then it's almost like we just shift them over. So B, C, D, E, A, shift, C, D, E, A, B, shift, shift. So that our 5th treatment E starts here, and then we go A, B, C, D, E. Now, what we're going to do is we're going to relabel the columns and rows. So instead of saying 1, 2, 3, 4, 5, I make rows L1, L2, L3, L4, L5, columns K1, K2, K3, K4, K5. So all I did from here to here was just give them new names. Now, our next step is to come here and we're going to permute the rows and columns. So in R or jump, all I did was shuffle these 5 rows and shuffle these 5 columns and put them back. So again, notice from here to here, the inside isn't changing. The A, B, C, D, still the same. We're just changing these rows and column labels by shuffling them. Now, from step 3 to step 4, we just organize it by putting it back into a cleaner version. So 1, 2, 3, 4, 5. Now you'll notice that the labels inside have changed. And what they correspond to is row 1. So here's row 1. Column 1 is C. So this C is now here. Row 1, column 2, because this is what that 1 and 2 are representing, is B. B's right here. Row 1, column 3, D, D. Row 1, column 4, A, A. And so then that's how we end up getting that shuffled. So now that we have the basic idea of a Latin squared design, which is 1 treatment, 2 blocks, where our treatments are assigned using an interlocked randomization, and this is what I meant by interlocked. Think very Sudoku puzzle-like. Let's start talking about our summary statistics, our statistical model, and our ANOVA. So we still have our response represented by Y, and we have IJ. And what this is going to represent is the response for the experimental unit in row I and in column J. And the reason we only need 2 subscripts is because if you tell me the row and the column, we can uniquely identify the observation. We also have KIJ, which is going to represent the treatment assigned to the experimental unit in row I and J. So for an example, if we had I1 and I equal 1 and J equal 2, and we came back up to our secretary example, we would go to row 1, secretary 2, we had treatment B, and then whatever this observation response would be. I haven't given you any data, that's going to come in one moment. We also have our summary statistics here where we can find the sample mean for the row I, the column J, our sample mean for treatment I, so K, and then we can also get our grand sample mean. So if I was to give you all data for our spreadsheet example, it would look maybe something like this, where we still have our rows and our columns. We have our treatment, and then here's our response for time. Our column means are represented right here. So that's just taking the average, putting it here, taking this average, putting it here, average, average. We also have our row means, which is averaging across this way. Then we have our treatment means. And what our treatment means are going to do is it's going to average all of a specific treatment. So for treatment A, it's taking these 4, averaging it to find here. So don't, it could be a little bit misleading, the fact that treatment A is under column 1, but this A is related to taking the average of these 4. Let's just do one more example to make sure it's clear. For treatment B would be averaging, where's B? Those 4 numbers and getting that. So don't let it be confusing that it is under column 1 and 2. That's not how it's related. I just needed somewhere to put it. We can also look at our treatment assignments by looking at the row and column labels. Here's how you would calculate your treatment means. Our treatment mean for alpha is 0.045, and we just talked about it, but this is looking at it through a mathematical notation rather than highlighting. Our statistical model is for a Latin squared is here, where we have our response, IJ, because we only need to know the row and the column to be able to uniquely identify the observation. We still have our grand mean. And then here are our model effects, which we would be end up plugging into jump or R respectively. We still have our random error, which is assumed to be normal, centered at 0 with some variance. Our alpha is going to represent our treatment effect. We'll use K as the subscript. B is going to be our row block, and gamma is going to represent our column block effect. All right, now our parameter estimates for a Latin square design are here. We have a lot of these should look very familiar. One thing I do want to point out is our cell mean right here. And so we're back to something that's similar to the randomized complete block design. Because we don't have replication within each block, we see each treatment only once, so we can't do that interaction with this model. And so a Latin square design is also additive. All our estimates here are unbiased. We have our treatment effects, our row block effects, and our column block effects. Notice one thing, our treatment effects and our treatment means aren't the same. They're 2 different things, so just be aware of that. We also then have our parameter estimates now help us to figure out the partitions of total sums of squares. Our total sums of squares is, again, measuring the variability of all the sources. It is going to be comprised of our sums of squares treatment, plus our sums of squares of our rows, plus the sums of squares of our columns, plus the sums of squares of our error. Again, you don't have to memorize these or actually have to ever compute these by hand. We have software to help us do that. The sums of squares helps us to get to our ANOVA table for our Latin square design, where we have our treatments, our row and column. Again, recall that our rows and columns are acting as a block. And so we aren't going to have an F statistic for both of those. This goes back to the same intuition that we developed when we were talking about the RCBD and how we don't test for blocks there. Notice that if we didn't have these blocks, that our sums of squares for rows and columns would be in our sums of squares error. Just like our previous classes and designs, our goal is to get the F statistic for the treatment and to be able to see if we can do compare the signal to noise. The only difference here with the Latin squares, we have 2 block factors. Hopefully, guys, will start to notice that once we set up our experimental design and we set it up properly, the analysis is relatively easy, assuming you put it in the computer right also, which can sometimes be difficult. This last little part is to help motivate why, again, we don't look at the block F statistic. We've seen this before. So our MS treatment, so our hypothesis is looking at this. Our alternative says at least one differs. One corresponding to alpha differs, doesn't equal 0. So we've seen this before. Our expected mean squared treatment under the null, this gets canceled out. So we have sigma squared over sigma squared, which is valid. In these two cases, which again are the blocks, do not have the sigma squared, so it's not a valid test. Now that we have an idea of what the Latin square design is, we've talked about how to do randomization, we talked about the model, and we've seen the ANOVA test. In our next lesson, we're going to go through the entire spreadsheet example using R and jump.